Hi, my name is Lauren Davis, and this is the Terahertz Crystal Classification Project. First, some background on some nonlinear optical crystals. A nonlinear optical crystal is a solid that can alter the frequency of light as the light passes through the crystal. So this is super useful in a lot of areas. Some of them include quantum computing, ultrafast communication, development of new laser technologies, and cybersecurity, just to list a few. I work in the Johnson Spectroscopy Lab on BYU campus, and we use nonlinear optical crystals as terahertz generation crystals. So basically, we send a laser through them, and light of terahertz frequency comes out, and we use that for 2D terahertz spectroscopy, bioimaging, and a bunch of other things. So these crystals, they're super valuable, but they're very difficult to design and synthesize. One of the requirements to be a nonlinear optical crystal is that it has to be noncentrosymmetric. This means that there's no inversion symmetry in the material. Here I've shown two examples of crystals. One is centrosymmetric on the left that does have an inversion center, and the one on the right is noncentrosymmetric, so no inversion center, and this one has potential to be a nonlinear optical crystal, a useful crystal. Unfortunately, less than 15% of all known molecules are noncentrosymmetric. So it's difficult to find them, and even if it is noncentrosymmetric, there's no guarantee that it'll also make a good terahertz generation crystal, for example. So in the past, it's been very difficult to design new ones because the main method for it is called the Edisonian approach, a fancy way of saying trial and error. So the approach goes like this. You modify a known nonlinear optical crystal structure. Maybe you add a functional group or change a few things in ways that you think might help. Then you go to the lab and try to make this molecule, synthesize it, and then take a long time to crystallize that material, and then take it to the spectroscopy lab to test it. And after all of that, the last step is just being disappointed, because less than 10% of the time, the material that results is actually noncentrosymmetric and useful. Big bummer. But the good news is that my project will help. In my project, I tested 8 different classifiers that took these input features, just molecular properties that you would know of your proposed molecular structure, and then output whether the crystal is going to be centrosymmetric or non-centrosymmetric. The goal being to put your ideas, your guesses for what's going to be a good crystal into this algorithm, and it can tell you without spending 8 months creating it in person whether or not it's going to actually work. So hopefully very useful in the lab. So the process for this project, first I had to do some data cleansing and preparation. So part of that meant gathering the data, both from the Cambridge Structural Database and from our own calculations. So I worked with Enoch Ho, who is a graduate student in chemistry here at BYU. He submitted a bunch of first principles calculations to the BYU supercomputer to get a lot of the properties of these materials. And in the end, we ended up with 49,643 samples that were mostly centrosymmetric, but 15,000 of them were non-centrosymmetric. So it took a while to combine all of the different files with different features in them into one pandas data frame, and then remove duplicates, outliers, and missing values, create new features. For example, this one on the right, I show molecular weight had this really large spread to it, where most of the molecules were down here like at a couple hundred molecular weight, grams per mole. But there were definitely some out here that had thousands of grams per mole, and I wanted to include those and be able to predict those. So I had to take the log base 10 of that feature to get this new feature, log 10 of molecular weight. That was much more useful. I also had to remove some unnecessary features. You can see from this correlation matrix that there were many features that were super correlated to each other and therefore didn't need all of them. For example, number of carbon atoms and number of bonds in a molecule. If it's just a big molecule, it's going to have lots of carbon atoms and lots of bonds. It's not very helpful to have both, so I got rid of one of them. All that was preparation for plugging this data into 8 different machine learning classifiers. So here they were: AdaBoost, logistic regression, XGBoost, k-nearest neighbors, decision tree, random forest, support vector classifier, and NLP. That's the deep learning neural network. So these are the confusion matrices for each of those. And you can see that SVC stands out with only 8 false negatives here, which is very exciting. We were not expecting it to be this good. We were getting less than 10% accuracy before this, so any improvement was very welcome. But we ended up with SVC at 98.6% precision. So real fast defining accuracy and precision. Accuracy is the number of true predictions out of all the predictions that were made, whereas precision in this case was out of all of the materials that we predicted to be noncentrosymmetric, how many of them actually were noncentrosymmetric. That's the metric that will really tell us how well the classifier performed, and that's what this number was here. Really astounding, very exciting, and here's how it compares to both what we were getting before with trial and error and to what a published paper was getting. So this paper was published by Song et al. In 2020, where they used the MAGPIE features dataset. It's not something that I think I had access to, so I had a different set of features to work with. This group only tested random forest and the multi-layer perceptron neural network as classifiers. One thing that they did do that I might want to try over the summer is tenfold cross-validation on their data to artificially boost the number of samples that they had and also reduce overtraining. And their value that they got in the end was 86.9% accuracy, which they didn't provide a precision value, but I think it compares favorably to ours. So in conclusion, we made significant improvement over our trial and error method in the lab and improvement over the published work by Song et al. It'll save us a ton of time and other resources in the lab, the Johnson Spectroscopy Lab, and potentially lead to our own publications, not only on this machine learning method itself, but also out of all of the new materials that we find from this method, each of those could lead to its own publication as well. So we're very excited about the 98.6% precision in this project, and that is it.